All right, another way we can use ice tables. This one gives us an equilibrium constant and asks us to figure out some concentrations. So, still want to set up an ice table. We're given the reaction. They're all gases, so we'll use them all. We don't ignore anything. There's no pure substances there. And we'll do our ice table down the side. This one says we start with 1 mole of CO and 1 mole of H2O, so our two reactants. The only thing though is always have to use concentrations in a ice table. So 1 mole in 5 liters. So 1 divided by 5 real quick, we'll do 0.2 moles per liter for each of those initial substances. Because it doesn't say anything about the products, we're going to assume that there's 0 initially. And there's the first part of our table done. Next part, we got to do a change, figure out some equilibrium stuff. Because our products are 0, that means they have to go up. They can't go down into the negatives. And because our product side is going up, that means our reactant side is going down. Now, we don't know how much it goes up and down by, so this is where it causes a little bit of a problem. And I'm going to put in X for my product. Now this reaction is really nice because it's a 1 to 1 to 1 to 1 ratio. So if CO2 goes up by X, that means the H2 has to go up by X. It also means our reactant each have to go down by X. So 1 to 1 to 1 to 1 ratio, the changes are all the same value numerically. And then we can put in kind of an equilibrium concentration. 0 plus X makes X. 0 plus X makes X. And then these ones we're going to leave as 0.2 minus X. So it looks like a pain. We got some algebra to do, but we'll see if we can figure it out here. Okay. Next step, equilibrium law. So K is equal to, remember it's always products over reactants, so CO2 times H2. These are both to the power of 1 because they have coefficients of 1, over our reactants, CO and H2O. Should be able to plug in some numbers now. Up at the top it tells me that my equilibrium constant is 0.83, so we can actually replace our K with 0.83, and then we can plug in some values here. Because CO2 and H2 are both X, we'll have X times X on the top, so I'll just simplify that to X squared. And then on the bottom, I have 0.2 minus X times 0.2 minus X, so we'll simplify that to 0.2 minus X squared. All right. You can see how this starts to get kind of a pain. You'll never have questions where you have to use like quadratic equation. We'll always be able to simplify or make a little bit of an assumption. In this one, what I would do is, because both of the things on the right-hand side are squared, I'm going to square root everything. So if we do the square root of 0.83, we get something like 0.911 with some stuff after it. And then on the other side, our squares just go away. So we're left with something a little bit more simple. Keep solving through for X here. I'm going to multiply both sides by my denominator. So these will cancel. And then I'll multiply this side by the same thing. And you can, distribute, get rid of the brackets. So this will end up like 0.1822 minus 0.911x. On the right-hand side, all I really have left is just x, and we're getting there. Let's put our x's together. So I'm going to add 0.911x to both sides. we got just our number now on the left-hand side is equal to, remember that this is 1x, so when we add those together, this is 1.911x on the right-hand side. And last step, we will divide by 1.911 both sides. Here we got x left over, and 0.095 is our x value. Go up to the top here. Oh, something got, we'll just pull this down here. There we go. This says what's the concentration of each substance when the gases are in equilibrium. So for these two values here, the x's, we know those are both 0.095 moles per liter, just what we figured out what our x value was. These two here are 0.2 minus that x value, so we get about 0.105 moles per liter. Pretty close, so it's pretty it's pretty close to a 50% reaction. Our equilibrium constant is a little bit lower than 1. It's almost 1, so favors the reactants just a little bit.